Theorem on eigenvalues and eigenvector. First, if n is positive integer, lambda is an eigenvalue of a matrix A, x be an corresponding eigenvector, then lambda raised to k is an eigenvalue of A raised to k, and x is what? Is corresponding eigenvector. So first of all, we are going to see one example here. Consider a matrix A. Consider matrix A is equal to here. A is equal to -1, 2, 2, 2 square 2 by 2 matrix. Then first of all, we are going to determine its eigenvalues. So for that, characteristic equation is lambda square minus trace of A into lambda plus determinant of A equal to 0. So it is lambda square minus trace of A, that is lambda, plus determinant of A is, so what is your determinant? It is -2 -4. So this is equal to -6 equal to 0. So its root are lambda minus 3 and lambda plus 2 equal to 0, and therefore this implies lambda 1 is equal to -2 and lambda 2 is equal to 3. So these are the two eigenvalues. Now next, if we determine its square, so what is here? A square? A square is equal to A into A. So it is equal to -1, 2, 2 2 and -1, 2, 2, 2. So A square is equal to, so the multiplication of this matrix is 1 plus 4, then -2 plus 4, then second row first column, so -2 plus 4, then second row and second column, so this is equal to 2 into 2, it is 4 plus 4. So if you simplify this, then A square is equal to, it is equal to 5, 2, 2, 8. Now if we again, if we start to determine its characteristic equation, then characteristic equation is again lambda square minus trace of A, so this is what? 5 plus 8 lambda plus determinant of A. So what is determinant of A? It is 40 minus 4 equal to 0. So this is lambda square minus 13 lambda plus 36 is equal to what? 0. If we simplify this, then this is equal to, again its roots are lambda minus 9, lambda minus 4 equal to 0. So this implies lambda is equal to 4 and lambda is equal to 9. So you can see here the eigenvalue of A square are lambda 1 square and lambda 2 square. So here you can check what is lambda 1 here, the eigenvalues of A. These are the eigenvalues of A. This is what? Eigenvalues of matrix A, and these are the eigenvalues of A square, eigenvalues of matrix A square. You can check, if lambda 1 is -2 is eigenvalue of A, then its square is what? 4 is its what? Eigenvalue. Similarly, lambda 2 is equal to 3 is eigenvalue of matrix A, then its square lambda 2 is -9 plus 9 is eigenvalues of A square. Now, so this is an example. So we are going to prove this statement for every matrix A, square matrix A. So if n is a positive integer and lambda is eigenvalue of matrix A, x is corresponding eigenvector. So what is your given? So the given part is, so given lambda is an eigenvalue eigenvalue of a matrix A with eigenvector x. And what is our claim here? Our claim is that lambda raised to k is an eigenvalue of a matrix A raised to k with an corresponding eigenvector x. That is what we are going to show here, that lambda raised to k A raised to k x is equal to lambda raised to k x. So now to prove this, now since lambda is an eigenvalue of a matrix A with corresponding eigenvector x, then from the definition of eigenvalues we can write Ax is equal to what? Lambda x. Now to prove this, we are going to use a mathematical induction here, using mathematical induction. So step first for say this is from equation start. From this equation start, step 1 for k is equal to 1, that is we want to show that x is equal to lambda x. So from start we can write x is equal to lambda x, and therefore for k is equal to 1 result true. Okay, now in step number 2 we assume that the statement is true for k is equal to r. R is what? R is less than k, so k is equal to r. That is, this implies a raised to r x is equal to lambda raised to r x. So this is equation number double star. Okay, now step number 3 we want to show that here. In step number 3 we want to prove that statement true for k is equal to r plus 1, that is a raised to r plus 1 x is equal to lambda raised to r plus 1 x. This is what we want to show here. Now consider LHS here. So what is LHS here? A raised to r plus 1 x. We can write this as we know that a raised to m plus n is equal to a raised to n. So we can write this as a raised to r, or a time a raised to r x. But what is a raised to rx? This is equal to a time lambda raised to rx. Why? By using equation number double star. You can check here. By using equation number double star, by using this equation, what is the value of a raised to rx? It is what? Lambda raised to rx. Here you can say by using equation double star. Now since lambda is a constant number, we can take it outside from the matrix A. So it is what? Ax. But again using equation number star. So what is star here? Ax is equal to what? Lambda x. So the value of ax is equal to what? Lambda x. Again this is nothing but the lambda raised to r plus 1 x. So a raised to r plus 1 x is equal to lambda raised to r plus 1 x, and therefore result is true for the given statement given statement true for k is equal to r plus 1, and therefore by mathematical induction we can say that a raised to kx is equal to lambda raised to kx. That is, result is true for every natural number k, and this is what we want to prove, that a raised to kx is equal to what? Lambda raised to kx.